Hi everyone, I'm Zhang from Hong Kong University of Science and Technology, and I'm here to present our work, BatchCrypt, which is tailored to improve the efficiency of cross-silo federated learning enabled with homomorphic encryption. This is the joint work between Hong Kong UST, University of Nevada, Reno, and WeBank. Machine learning relies on the abundance of data and complex models. In the past years, centralizing data first and then train models within data centers has gained huge success. However, such pipeline is facing new challenges. Recent years have seen a huge concern over data privacy, either due to data owners' reservations or government's regulations. It is more and more common to have the training dataset fragmented across multiple data locations, also known as data silos. As a result, federated learning systems are proposed to enable collaborative learning utilizing these small and fragmented datasets. For this work, we target the cross-silo horizontal federated learning setting. Cross-silo means that the data owners are a few organizations as opposed to cross-device setting where data owners are thousands of edge devices. In the cross-silo setting, data owners have reliable computing resources of their own compared with edge devices. Since the collaboration is among institutions like banks and hospitals, the data security requirements are usually more prominent. While the horizontal part means that the datasets all share the same feature space, as the picture shown here. Horizontal training is when the data from A and B share the same feature space, but differs in sample IDs, while vertical training refers to when the data from A and B have different features, but they all belong to the same IDs. The objective of horizontal cross-silo federated learning is to train a model together without leaking private information to each other or a third party, like an aggregator. One straightforward thought would be, why don't we just directly apply the data center distributed training technique, like parameter server here? However, as literature suggests, gradients are not safe to share in plain text. A curious person can easily recover a lot of information from only a small portion of the gradients, as shown in the picture. As a result, a couple of privacy-preserving techniques have been used to facilitate federated learning. The first one is differential privacy. It can be efficiently implemented, but its privacy guarantee is not strong enough for many applications, and it also suffers from accuracy loss, especially for non-ID datasets, like federated learning usually has. Secure multi-party computing is another technique. It requires sophisticated computation and frequent communication among the participants. So the overhead is very high. Secure aggregation is proposed to enable federated learning among thousands of edge devices, so it's not suitable for the cross-silo setting we have here. Homomorphic encryption is the option we explored in this work. It has the desired property of strong privacy guarantee and no accuracy loss, but it suffers from high encryption overhead. A little background on the homomorphic encryption here. Additively homomorphic encryption has the property of allowing computation over ciphertexts. For example here, adding the ciphertext of A and B and then decrypting it will produce the same result as adding the plain text together directly. This very convenient property enables oblivious aggregation, where the aggregator can perform homomorphic addition without seeing anything in plain text. As the figure suggests here, in the iteration, a client will compute gradients based on its own data and then encrypt the gradients before sending it over to the aggregator. the aggregator will collect all the encrypted gradients and perform homomorphic aggregation on them, and then return them to the client. The client can then decrypt the gradients and apply them to their model, to its model. So with homomorphic encryption, we can satisfy the objective of not leaking information to each other or to the third-party aggregator here. To characterize the performance of utilizing homomorphic encryption in federated learning, we analyzed the traces of a 10-node cluster and discovered that most of the time is spent on homomorphic encryption-related computation like encryption, decryption, or aggregation, while only a small fraction of the time is actually spent on the model computation. Why is homomorphic encryption so expensive? Homomorphic encryption requires heavy numerical computation of long integers. And at the same time, regardless of the plaintext bit width, the ciphertext is almost close to the key size. And in the modern day setting, a minimum size of 2048 is recommended. So homomorphic encryption has both high computational and communicational overhead, making it almost impractical to train a state-of-the-art model in production with homomorphic encryption. In the table here, with a small model of 7 megabytes, it takes almost 20 minutes to finish the encryption, and the ciphertexts are more than 7 times larger compared to the plain text. To alleviate homomorphic encryption's overhead, an intuitive solution will be accelerating homomorphic encryption itself, right? Unfortunately, homomorphic encryption has limited parallelism. Even with specialized hardware like FPGA, the speedup is very limited. Another approach will be reducing the encryption operations altogether by allowing one encryption operation process multiple data points, aka batching. We first batch the multiple gradient plaintext into a long plaintext and apply only one homomorphic encryption operation on it. With batching, besides reducing the number of encryption operations, it can also address the mismatch between short plaintext and long ciphertext. Now with the longer batch plaintext, overall communication won't be significantly increased. However, the challenge remains, how do we maintain homomorphic encryption's additively property? Decrypting the sum of these two batched ciphertexts should still match the results of adding these pairs individually. The catch is that on the aggregator side, there are only ciphertexts available, so the aggregator cannot differentiate, shift, or permutate underlying bits. The only operation aggregator can do is just plain bit-by-bit addition. Since gradients are floating points numbers, the addition cannot be performed within a batch, as there is no way for us to align exponents within the ciphertexts. Since floating points values are not be able to be batched, one intuitive solution would be quantization. A generic quantization scheme can map a real value from -1 to 1 to integers from 0 to 255, and the aggregated results can be translated back to the rational form following this procedure. However, such quantization scheme is proposed to compress model sizes, not for aggregation. So when we apply it directly to aggregation, we will face many limitations. First, to dequantize, client numbers must be known as shown here, but such number might be shifting and even available in many cases, like when flexible synchronization scheme is adopted. Secondly, it overflows easily as we are adding positive numbers together. Lastly, there is no way to tell a negative overflow from a positive one. Driven by the listed limitations, we aspire to devise a quantization scheme for federated learning aggregation, we want the new quantization and batching scheme together can be both flexible and overflow aware, which means after batching and aggregating over batched values, the results should be easily unquantized to the original forms without additional information. And when overflow happens after aggregation, if we are able to differentiate the positive overflows from negative ones, we can use a saturated value for this run instead of discarding the computation whenever overflows happen, which can improve the overall efficiency. Pushed by our design objectives, we summarize the requirements as signed, symmetric, and uniform. To be able to distinguish overflowing, the quantized values have to be signed. And in order to allow direct addition of quantized values, the quantized range must be symmetric and uniform. For example, here, we quantize floating numbers from -1 to 1 to integers from -1 to 7 to 1 to 7. So in the example here, real value of -0.0079 will be quantized to -1. And the same happens here, which is quantized into -1 to 6. And by adding the quantized value together, we get -1 to 7, which can be dequantized easily back to -1, which is the correct answer by adding the plain text, adding the original forms together. With quantization requirements concluded, how can we batch the quantized values into long integers remains the challenge. With 2 signed bits instead of 1, we can determine the overflowing situation just from the aggregated results alone. But introducing these signed bits require us to be able to somehow perform addition without knowing which are the signed bits and which are the value bits. Inspired by modern others implementation, we adopt 2's complement coding to enable oblivious addition. Lastly, to absorb the overflowing sign bits in between numbers, we pad zeros in between values. As shown in the example here, after we have the quantized value -1 and -1 to 6, we can translate them into their corresponding 2's complement form with 2 sign bits, and we can form long batches with zeros padded in between. After that, with 2 long batches, we can just perform bit by bit plain addition and get the result in the end. And we are able to simply translate the aggregated results back to the quantized form, -127, which can be further dequantized back to the correct answer, -1. Now that we've figured out how to concatenate quantized values, there is another hurdle. Gradient values are unbounded, while quantization range is. So clipping is required before quantization. Clipping refers to the process of saturating the outlying threshold, the outlying values beyond the threshold alpha to alpha. The clipping threshold alpha here is an important trade-off now. Smaller alpha leads to a higher quantization resolution within the threshold, thus leads to a lower quantization noise. But at the same time, it will cause more diminished range information outside of the threshold, leads to higher clipping noise. Since clipping is important to achieve a good quantization quality, there are generally 2 ways to determine the threshold here. A profiling-based approach has been used widely in a conventional clipping setting. We will feed a hand-selected dataset into the neural network and try a few candidate alphas until we find the best one. However, such approach is unsuitable for federated learning. First, it is hard to find a sample dataset, as federated learning typically has non-IID datasets, and centralizing these samples dataset will violate the privacy requirement as well. Second, gradient range diminishes during the training, so array profiling will be needed after every few rounds. So instead, analytical clipping, on the other hand, is a better fit for federated learning. It models the clipping noises with distribution fitting, and it is more flexible and adaptable to gradient range changes. Gradients are well known for having a bell-shaped distribution, so we attempt to fit it into Gaussian distribution. However, conventional Gaussian fitting is an ill fit here. Methods like maximum likelihood estimation and Bayesian inference require a lot of information and is computationally expensive, making it hard to adapt quickly in distributed federated learning setting in an online manner, as it adds significant computation and communication overhead to the workload. We propose an analytical gradient clipping model for distributed datasets called DACIQ. It efficiently fits distributed gradients to a Gaussian distribution with a much faster method with less communication required. And we then minimize the accumulated clipping and quantization noise in an online manner. To further optimize the quantization quality, DACIQ also utilizes stochastic rounding and layer-wise quantization proposed by literature. We designed and implemented BatchCrypt atop Fate, which is the most starred federated learning framework on GitHub at the moment. DACIQ module here will first compute the optimal clipping value for the iteration, and then the quantizer will quantize the gradients accordingly. The quantized values that are then translated into 2's complement encodings and then batched into long integers. In the end, the batch integers are encrypted with Homomorphic Encryption manager. The decryption process happens in the exact reverse order. We implemented BatchCrypt and evaluated with 10 machines spanning across 5 EC2 data centers across multiple continents. And we use 3 diverse machine learning workloads of various sizes as the test models here. We first examine how BatchCrypt's quantization affect model quality. We plot the test accuracy for fairness and cipher, while loss for LSTM, as we can see in the figure, with appropriate quantization bit width, usually larger or equal than 16, there is negligible accuracy loss. And in some cases, the quantized version even outperformed the plain version, as stochastic rounding introduces randomness that can act as a regularization process. This shows very promising improvement potential, as with the recommended homomorphic encryption key size of 2048, the batch size can be set to more than 100 when the quantization width is 16. So we are expecting 2 orders of magnitudes of acceleration in an ideal setting. We then compute the computation breakdown, compare the computation breakdown of BatchCrypt against Fate's stock implementation. We use 16-bit quantization and set the batch size to 100. We plot the time breakdown as well as the overall time in the figures here. As we can see, BatchCrypt can significantly reduce the computation overhead by up to 92.8 times. And with larger models, it is easier to form larger batches. As a result, the speedup is larger. While reducing the computation overhead, the communication overhead is substantially reduced as well. As shown in the figures here, we plot the overall traffic occurred in each iteration. With the help of batching, the mismatch between short plain text and long ciphertext is no longer the case. As a result, the overall communication is almost reduced to the same size as plain text gradients. With the larger model, the reduction is bigger as well. In the end, we compare our performance with the most optimal baseline, plain distributed training without any encryption or other privacy guarantees. We plot the iteration time on the left, while the overall traffic on the right. As we can see, the slowdown introduced because of homomorphic encryption is reduced substantially to an acceptable magnitude for real-world deployment. After comparing BatchCrypt's performance per iteration with stock fake and ideal baseline plane, we compare the total time and communication required until convergence under each scenario. As shown in the table, BatchCrypt achieves remarkable time and traffic reduction at no cost of convergence quality. With BatchCrypt, it is practical to train a state-of-the-art complex model with acceptable overheads while enjoying the benefits of that homomorphic encryption provides. In conclusion, with this work, we characterized homomorphic encryption-enabled cross-silo federated learning. We designed an efficient homomorphic encryption batching scheme called BatchCrypt, which co-designed quantization, coding, and batching. And we also designed an analytical clipping method called DACIQ for BatchCrypt. We implemented and evaluated BatchCrypt with AWS EC2 and achieved up to 99% cost reduction compared to the stock implementation. Thank you all for coming to this presentation. BatchCrypt is open source at the following link. And if you have any more questions, please don't hesitate to reach me through the contacts listed on my personal website. And I'll be graduating soon myself. So if you have any opportunities, please reach out. Thank you very much.